Oh, and then that's determinants. I thought I had another example here. We did actually all of that. Okay, so we're on determinants now. Oh, that's great. So it's really kind of a misnomer where I call it intro to determinants, because we've already been introduced to the concept. It's just a matter of, like, can we expand beyond letting the calculator find the determinant for us, and also can we expand beyond just 2 by 2 square matrices, right? So that's really what the challenge is going to be now. Right? Before we get into that, we have to talk about permutations. Right? Honestly, I played around with this lesson a lot, and I've reorganized and rewrote, and I honestly just don't think that there's a nice, convenient way to type up this concept in a way that's simple and to the point, right? But it's a concept that actually is kind of simple and to the point. It's just, when you see all the notation, and especially the summations, and it's like, how could this be simple? It looks like we're in for a ride. It looks like I'm about to torture you for the next hour or so. But really, it's not too bad. But I do have to kind of at least walk you through some of it. Okay? And the concept of a permutation is the most important piece, because that's going to drive everything related to determinants. I will say, before I started teaching this course, I had no idea that there was a difference between an even and an odd permutation. I did not know that that was a thing. So that means that I took linear algebra, I took probability and stats, actually 4 different versions of that course, 4 different levels, different institutions, and it somehow just never came up. I think when I was learning about determinants, it was really just, for me personally, maybe the teacher was talking about it extensively. I think me personally, I wasn't at the point where I was overly interested in the why. I was, like many people, only concerned with the how, right? And so maybe it was addressed, but that's probably when I shut my brain off in class, and it is what it is. So I'm just going to go back to early probability and talk about the concept of a permutation just very quickly. So, quick example, and I'm just going to keep it very basic. If I want to rearrange the letters A, B, and C, I want to come up with all the different possible ways to rearrange, right? I could do it a couple of different ways. One way would be to just kind of reason it out and say, well, A, B, and C, that's one arrangement, and maybe A, C, B, then B, A, C, have some kind of systematic approach. But I could also do a tree diagram, right? If I do a tree diagram, it's just A, B, C. If A is the first value, then it could be either B or C that's the second value. If B is the first value, then it could be either A or C as the second value. If C is the first value, then it could be either A or B as the second value. And then whatever's left over would be the third value. So C, B, C, A, B, and A. All right? So we're looking at 6 arrangements. Now, if we were sitting in a probability class, I'm trying to remember if I've taught this in my stat class yet, or if I'm teaching it to them this weekend. But it's funny how all the courses, they all just kind of line up, where what you need to know in one class, I'm teaching in another class. It always just plays out that way. So like in Calc 3, we're talking about continuity for a vector valued function, so in 3 dimensions. And so what I was teaching in Calc 1, how to determine continuity. Like same day, it always plays out that way. Right? So, and I wish I could say I plan it out, but I don't. I'm not that good. So So yeah, if you're taking a stat class right now, odds are you're probably learning about this very concept. So you would be saying, okay, well, if I want to have 6 arrangements, or I want to determine the number of arrangements to be 6 without having to list out all the possible outcomes, I could use a factorial. 3 factorial is the same as saying 3 times 2 times 1. All right, a factorial is a type of permutation, right? So it's the simplest kind. It's where there's no restriction on the number of elements that could be in your arrangement. It's the musical chairs case, all right? So the number of ways the individuals could sit down in the chairs, but you're leaving all the chairs there. The number of chairs match the number of peoples. That's funny. I can't believe I just said that. All right, but whatever. It's a day for it. Why not? But yeah, so yeah, the number of chairs matches the number of people. That would be a full-blown factorial all the way down to 1. Now remove a chair and you're creating a restriction. Remove 2 chairs, you're creating even more of a restriction. So you would determine how many different ways you could have winners and losers and things like that, right? So how does this tie in here? Well, when we're determining products as part of a determinant or even matrix multiplication, we are basically just trying to figure out all the different ways in which we can multiply entries from one matrix to another or entries within the same matrix. All right. In order to do that, what we do is we figure out the number of different ways that we can rearrange the columns of the matrix. All right. So in this case here, my example is I have a 3 by 3 square matrix. You know, I didn't include that context because all I care about is the number of columns. I have 3 columns. The numbers 1, 2, and 3, just like A, B, and C, could be rearranged a total of 6 times. Right? So that gives us all of the different permutations that we could have of the numbers 1, 2, and 3. But we develop what we call even and odd permutations based on the number of inversions that you would need to make in order to get from your base set 1, 2, 3 to the entry in question. Like for example, going from 1, 2, 3 to 1, 2, 3, I don't have to use any inversions. And all I mean by inversion is swapping adjacent values. All right. So to get from 1, 2, 3 to 2, 1, 3, all right, I would have to swap the 1 and the 2, right? That's 1 swap, so 1 inversion. To get to 3, 1, 2, I'd have to make 2 swaps, right? First, and I'm not showing it here, so that's why I was saying that, like, to type this up, it just makes it confusing. I'm just showing you 31 and 32. You look at that and say, I don't know what that means. So at least for this one, maybe just off on the side, you show the progression. 1, 2, 3. The first thing you would do is swap the 1 and the 2. So that's 1 inversion. And then swap. Oh, actually, I swapped the wrong things. Swap the 2 and the 3. So you get 1, 3, 2. And then in the next step, swap the 1 and the 3. And that'll give you the 3, 1, 2. All right. So you have to make 2 adjacent inversions in order to get from 1, 2, 3 to your desired number 3, 1, 2. All right. So some of them are obvious and some of them are not so much. Like to get from 1, 2, 3 to 3, 2, 1, I have to actually make 3 inversions. All right. The number of inversions it takes to get from your base set to the desired numbers is going to dictate whether you have an even or an odd permutation. All right. So none, 2, well, none or 2 in this case, but any of the evens would get a positive sign. Any of the odds would get a negative sign. All right. So that's the key step, because if you think, and I'll just show you really quickly. because this, again, you look at this and it's like, oh my God, well, what is this supposed to mean? But when I show you the example, it's going to make a lot of sense, I think.
What do you mean? So you're saying like the odds are a negative sign?
Yeah, we're gonna. I'll show you what that means in a sec.
Okay.
Right? Because when we found the determinant of a 2 by 2 square matrix, so I'll just kind of chuck that in here. So I want the determinant of a sub 1 1, a sub 1 2, a sub 2 1, a sub 2 2. So the determinant of this was just a sub 1 1, a sub 2 2 minus a sub 2 1, a sub 1 2. All right. So the question that might have been floating around in your mind would be why subtraction? Right? And the reason why we have subtraction is because we have a negative permutation here. All right. So here I'm taking the numbers 1 and 2, right? So the numbers 1 and 2 make up my set. I would think about the different arrangements of the numbers 1 and 2. You could have 1 and 1, because we allow for repetition, right? 1 and 2, 2 and 1, 2 and 2, right? So if we just focus on the ones that are not the repeated values, because those end up being irrelevant, we have 1 and 2 in the same order, so no inversion. 2 and 1 is the reverse order, but it only involves 1 inversion, right? So 1 inversion no inversion. I just locked myself out. So I can't undo the fact that I just horribly spelled inversion incorrectly. Why am I locked out? Oh, there it is. Okay. All right. So if I'm looking at the even cases represent a positive value. All right, so this is going to be positive. Odd inversions are negative. So when I'm finding products of values, just based off of the different arrangements, when I get to the part where I'm multiplying the a sub 2 1 by anything, I'm looking at a sub 2 1 multiplied by a sub 1 2. I'm taking a negative and a positive and multiplying them together. Negative times positive is going to give a negative. All right. So the other two again end up being a relevant question.
Yeah, you said why it's negative?
It's negative because we have 1 inversion. So odd number of inversions give a negative value. Right?
And you're not even counting the repetitions.
And we exclude the repetition, and I'll get to why that's the case later. All right. So that's really, I mean, it's kind of crazy to think about it, but that's what all of this stuff here is trying to say. Right? It's like, you see all the notation, and it goes back to one of the first things I said on day 1 of the course. Like, a lot of the things that we do in this class, it's not challenging, the math part of it. You know, it's just understanding what the hell you're being asked to do, right? So, like, when we talk about it, like an adjugate later on in the course, like, is that even a word? Like, is it a word that's designed to, like, test your ability to memorize facts? I don't know, but I'll try to give you some context. And then of course you got the ones that are named after people. So we use row reduction or elimination, reduced row echelon form, but it's called Gauss-Jordan elimination. So you see that and you're like, wait a minute, is that any different from what we've been doing? No, it's just the proper name for it. So like when we talked about a Jacobian matrix later on, I mean, I don't know that you could look at the title Jacobian matrix and think to yourself, oh, that clearly must involve derivatives, right? So that's the big challenge here. But there's also the part where, dang, I didn't even know that existed. And from my perspective, that's a true statement. Before I taught this course, I didn't even know that was a thing, right? Because it's never relevant in the courses that the other courses I teach. In a prob and stat course, probabilities need to be positive numbers between 0 and 1. So a negative permutation would never even come into play, all right? So yeah, but it's here. So just add it to the list, you know. And so we're going to use this to develop a set of approaches that we can use to find determinants, right? And one of which, you know, we'll kind of flesh it all out. But one technique is going to be the winner, the one that's better of them. All right. So basically, I mean, I typed it all up here, but like I said, we're looking at, you know, it's all well and good to have it typed out, but without the explanation, it doesn't really mean too much. All right. So same deal. Like, I mean, proof of the 3x3 determinant. The number of rearrangements of the columns J, giving us the different inversions, and then giving us this expansion as, bless you, as your method for finding a determinant. So what we get out of it, and this is really just, I produced this here for you just for shock value. All right, that's really the only reason why I share this with you. I would never ask you to generate this proof on a test, right? Because there's just so much going on with it. There is even a shortcut based off of this approach. If anybody had experiences with determinants prior to this course for a 3x3 matrix, you might have learned the shortcut trick for just reproducing the first two columns outside of the matrix and then just using diagonal down, diagonal up. It's a cool little trick. It's completely based off of this idea. And that's wonderful, but I got an even better technique for you, all right? So you could use that, but I would say, listen, if you're gonna use a technique that just basically asks you to multiply numbers and subtract them, then how is that any better than just typing it in a calculator and asking it to find the determinant for you? All right, so we want something that's gonna be even better. All right, so, but it might be surprising to think that this is the thing that's even better. If you look at that and say, oh, how is that going to be better? It actually is a beautiful formula that's going to get the job done for us no matter what the size of the matrix is. All right, so I'll just read it through first and then talk to you about what each component is really addressing. And then you'll see that it's actually kind of a nice thing. So for n greater than or equal to 2, right? So we need to have 2x2 square matrix or higher. All right, so what this is saying is that this would not apply for a 1x1 square matrix. All right. But then again, you don't need a fancy formula if you only have a 1x1 square matrix. It's just one value. I would probably, I don't know if I'd bet all my money, which is not a lot, but I'd bet a good chunk of it that anybody could, if I were to give you a 1x1 square matrix and ask you what value you could think of that describes that matrix, that you could probably come up with that. All right, so obviously it's for the more advanced cases. And once we get through this, you can test it out for the 2x2 and see that it works, and then forget about the 2x2 shortcut rule because this is even better. All right, it's the sum of the, so matrix A is the sum on n terms of the form of plus or minus a sub 1j, so not I, but 1j, times the determinant of a sub 1j, with plus and minus signs alternating, right, where the entries given are from the first row of A. All right, So I'm dictating specifically that I'm only working with the first row of A, and that we're letting the columns vary, all right? So that's an important component, all right? We define A sub 1j as a matrix that results if you were to cross off row 1 in column J. This allows us to define the determinant of an n by n in terms of n minus 1 by n minus 1, right? So we're taking the matrix that we're given and breaking it down into a simpler matrix, right? If you think back to pre-calc and calculus, whenever you were working with the rational root theorem, you know, synthetic division, you had to factor your polynomial. What you needed to do was come up with something that worked in synthetic division. Like, let's say you were working with something that was x to the 7th power. You needed to get it down, simplify it down until it was quadratic. Once it was quadratic, once it was degree 2, then you had a bunch of different techniques. You could use factoring, you could complete the square, you could use quadratic formula. This is really the same idea. You want to get it down to degree 2, because once it's degree 2, you have other strategies that you could use to find the determinant. All right. So what I'm going to do here is work through row 1, and we're going to create what are known as cofactors. All right. So based off of the elements of row 1. And again, as long as we account for all possible n minus 1 by n minus 1 matrices, we'll have a set of matrices that linearly combine to give the true determinant. There we go. Okay, so yeah, I basically rewrote the whole thing again just to replace the n with a 3. Right? So what you should appropriately glean from that is, okay, I don't have to rewrite the formula just to replace the n with the upper bound. But we're looking at -1 raised to the 1 plus j. All right. Now we have to progress our way from 1 to 3. So what this is going to mean notation-wise is -1 to the 1 plus j. The first j value is 1. So 1 plus 1. A sub 1, 1. Determinant A sub 1, 1. That little piece, that second piece, or I'm sorry, the third piece, the determinant part, that's the part that's going to make this all work, but it's also the part where it doesn't look like you can really do anything, but there's actually a lot you can do. All right. And then adding to that, -1 to the 1 plus 2 times A sub 1, 2, determinant A sub 1, 2. And then finally, everything is going to be the same except it's going to be 1, 3. All right, so that's what that summation is expanding out to. Now, parts of it are pretty easy. Some parts of it, So you don't really notice how obnoxiously loud something is until it stops. Now, I would imagine that if that went the entire period, I don't even think I would have noticed it. But like, the absence of the sound is now deafening. It's crazy. So -1 to the 2nd power. And then A sub 1, 1 is 1, but I still need that determinant part. -1 to the 3rd. Then we have a 5. Then a -4. All right. So in this blurb, in this mess of a blurb here somewhere, my attempt to make this as clear as possible, somewhere in there it says that the signs are going to alternate. it's not really a fact that you need to memorize, because what we're dealing with is an alternating series. All right, well, this is this is not an infinite series, but it's still a series. All right, it's alternating because you have -1 being raised to a power. All right, you're starting off being raised to an even power, so -1 becomes positive, then odd, so then negative, so it becomes negative, and then even again. So you have your alternating concept there. So what this is telling me, when all is said and done, is that I'm looking for the determinant of a sub 1, 1. Then I would have minus 5 times the determinant of a sub 1, 2, minus 4 times the determinant of a sub 1, 3. But still have not really gotten to the part where we would know what that even means. All right, so what we're going to do is go back to the matrix and just take a quick look. All right, and again, somewhere in this mess of a blurb, we talked about the idea that the determinant of a sub 1, 1, or whatever it is, a sub anything, is the determinant of the matrix that you would get if you eliminated the row and column that that entry is in. All right, so I'll color code it. Here's a sub 1, 1. I'm going to eliminate, here's my 1. I'm going to eliminate the first row and the first column. When I do that, I have a 2 by 2 square matrix. The dimensions of your resulting matrix should always be 1 less than the dimensions of the one that you started with. All right, so this is going to give me a 1, -1, 2, 0. Then we have the minus 5. Then I have to do the same thing for the 5. All right, so eliminate the row and column that contains the 5. Now, you start crossing out stuff too much, you can run into a problem. But I can still see that that's a 0 here. And that's a, I hope it's a 1. So 0, -1, 1, 0. All right, worst case scenario, you just erase it and do it again.
So I usually do this for like the first row of any matrix, I'd say, to find the determinant.
To find the determinant, you work across the first row. But at the risk of stealing my own thunder, as it'll turn out, it doesn't matter what row you work across.
Yeah, because you can always like switch.
Because you could always switch rows. All right, so that's going to allow us to streamline things pretty significantly, because like zeros are our best friend, right? So if I had a choice in the matter, what I would prefer to do is work across either row 2 or row 3, because then that's going to create a coefficient of 0, which is going to wipe out an entire linear pair, right? So I got my minus 4. Now I just need that last piece. So identify the row and column that contains that -4. Well, we already know the row. The matrix that results would be 0, 1, 1, 2. All right, so we can see here that we're looking at a linear combination of determinants. So I just have to figure out each of these determinants. So for this, you could go one of 2 ways. Do it again using the expansion technique, which I think is overkill, because we know in a 2 by 2 square matrix, it's just diagonal down minus diagonal up. All right, so 0 minus -2, so 0 plus 2 is 2. Minus 5. Then we have 0 on the down, minus a -1, so plus 1. Also 0 on the down, but this time minus 1. All right, so we can get the determinant here as 2 minus 5, so -3, plus 4. which is equal to 1. So the determinant of this 3 by 3 square matrix is equal to 1 using this cofactor technique.
How you get the 2 and the 1 and negative 1?
Multiply down the diagonal and subtract from it the product up the diagonal.
Oh, the from.
Yeah. All right, so I always feel the need to justify when we do stuff by hand because the calculator does just so much for us. And then, you know, like you expand it into other forms of technology, computers and things like that, it does it for us. So why do we have to do this by hand? Well, the answer is we're going to get into some cases that involve variable components to a matrix, right? And so when that's the case, you can't just chuck it into the calculator. And so that thing I was talking about before, the Jacobian matrix, it actually has applications in multivariable calculus. It's a pretty significant technique for working with volumes and areas in 3 dimensions. All right, so we're going to get to that before the course is over. In order to be able to do stuff like that, we need to be able to manipulate matrices with variable components, not just numerical components. And actually, we can perform transformations on polynomial functions using matrix operations. We just need to know how to define a matrix that represents a polynomial. But it's not difficult, it's just another skill. So once we do that, again, learning the value of a matrix determinant, like, we would want to apply that concept to the polynomial cases also. So there's a rationale behind this, right? Because I tend to not want to do things just for the sake of doing it. But like I said, this isn't that bad as long as you know what row to expand along, right? So use a cofactor expansion along the 3rd row, for example. So it's the same problem, if I'm not mistaken. Yep, that's what I intended anyway. You could do it across the 2nd or the 3rd row and make your life a little bit more convenient. The idea, again, is to know what the progression is, because we know that the signs are going to alternate. It's just a question of, is it going to be positive first or negative first? Right. So for that, you know, we can kind of cut to the chase a little bit, but we don't want to skip too many things. All right. So we're looking at, just again, the general formula, -1 to the 1 plus j. All right. So this is j equals 1. We have j equals 2. And j equals 3. All right, so -1 to the 1 plus j, when j is equal to 1, we're going to get a power of 2. Result is going to be positive. All right, then it'll go to negative for j equals 2. And then for j equals 3, it'll go back to positive. All right, so what we get from this is, yeah, the formula is great, but if we know that we're always going to have to start in the first column and work our way through all the different columns, and it's always going to be column 1 added to the one that's in the exponent, then we're always going to start off with a positive. So now I don't have to worry about that -1 component anymore. All right, so again, the idea is just to streamline this. So if I'm looking for the determinant of A, I know it's going to be positive, negative, and positive. All right, across the 3rd row, I got a 1. Then I got a 2. Then I got a 0, which is why I selected the 3rd row to begin with. All right, a choice between 2nd and 3rd row, could have gone either way. The fact that the 3rd row had non-negative values in it, that spoke to me, so that's what I went with. All right, so when dealing with column 1, all right, so the j equals 1, we're disregarding column 1 and row 3, which means that these elements are what are going to make up my matrix. All right, so we're looking at 5, negative 4, 1, negative 1. Then for the second one, we're ignoring the middle one, so I want this one and this one. So 1, negative 4, 0, negative 1. And then the last one, I'm just going to ignore. I'm not going to write a matrix out just to cancel it. So I'm just going to, I know the coefficient 0, so that's where I'm going to leave it. All right, so diagonal down, negative 5. Diagonal up, negative 4. Negative 5 minus negative 4 is the same as negative 5 plus 4. So negative 1 minus 2 times diagonal down is the only relevant piece here because diagonal up is going to go to 0, so negative 1. So we're looking at negative 1 plus 2, so positive 1. All right, which is what we expected because it's the same problem we did before. Now, it's not a proof, but it's a nice justification showing us that we could have gone down across the first row or the third row and we're still going to get the same answer. So maybe if you want to convince yourself, you go across the middle row and see if it ends up being 1 also. All right. It's kind of deceptive because it looks like, you know, based on what I did here, whoa, this is much easier than what we did before. I wouldn't say much. It's easier. It only seems like it's much easier because I didn't write all this stuff out. If I could have wrote all that stuff out for row 3 as well, you know, notation form, plugging in values, back to notation form, back to plugging in values, and then simplifying just to get to this part. But, you know, if you kind of get the concept, there's no point in doing all that, all right? But you could also see how this could be problematic if you have, if you're given a 4x4 matrix, because by expanding, the best you're going to come up with are 3x3 matrices, which you then have to expand further. All right, so increase the degree of the matrices, and you're definitely increasing the difficulty level. All right, if I gave you a 7x7 matrix and told you to find the determinant using cofactor expansion on a test, that might as well be the only question. All right, because that's all you're going to have time to do. All right, unless I make it so that there's zeros pretty much everywhere.
Wouldn't that number of operations still increase with the first formula that we used though?
With the first formula.
Because the first formula versus the cofactor expansion is still treating it as a 2x2 matrix to get the determinant.
The first formula is still treating it like the first formula as in this formula?
Mm-hmm.
Yes.
So there's no speed loss or gain with an increase in the size of your matrices versus one approach versus
Correct, yeah.
Right, question too. Like when you said J equals 1 and that's positive, like what do you mean? How were you doing?
If I plug in a 1 for J, you get
Awesome.
negative 1 to the second power. Makes it a positive number.
I think we were talking about like
The permutation stuff?
yeah.
Yeah, no, that was just to justify why this technique works to begin with. Okay, that's more of the foundational stuff. So then, of course, yeah, like right on cue. Look at this baby. I'm not going to do it with you right now. I'm going to put a star on it, but I don't want to torture you either. So let me just ask you right off the bat, which row do you think is the best row to work with here?
The last one.
The last one. All right. So when you choose that row, it's gonna simplify very nicely, very quickly. So you look at something that's kind of terrible, and it actually ends up being all right.
Would you be able to still use the same method as the 2x2 matrix when you're finding the determinant?
Once you get it down to 2x2 matrices, yeah.
Oh, okay.
So multiple steps here. All right. But you got this bad boy, this nice little nifty rule here. It says if A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal of A. All right, so in this case, you see I have a triangular matrix. This is upper triangular. All right, so the determinant of A is just going to be the product of 1, 2, and 3.
Does that apply for a lower triangular as well?
Lower triangular also. So any triangular matrix it's going to work for. So now, once we have that idea in hand, you know, cofactor expansion is something that you definitely want to practice, because if you saw the breakdown for the test, there's a question on it. It's going to ask you specifically to use cofactor expansion. So you got to know how to do it. But if I just needed to know the determinant, well, this isn't upper triangular yet, but maybe a couple of row operations makes it upper triangular, right? Because if I can just get rid of this 2 and this -2, then it would be upper triangular, and then all I'd have to do is multiply down the main diagonal, right? So that would be pretty nice. So try it with cofactor expansion, but then also try performing a couple of row operations to see if you can get rid of the 2 and the -2, and then multiply down the main diagonal. You'll see those two values are the same. All right. So it's a nifty nifty approach if you recognize it. So now that we learned everything there is to learn about determinants in record time, no, that's not really the whole point of this. Yeah. The properties, really, I mean, operations are wonderful. The justification, again, for why we learn about cofactor expansions, because we're going to use that for something more advanced later on. But we also need to know properties of the determinant. And any of these properties could work its way onto the test as a proof. All right, so like, for example, the determinant of A and the determinant of the transpose of A are always going to be equal to one another. All right, so how would you prove something like that? Well, I guess the important thing to be aware of is that it really does depend on what size matrix. If I'm trying to prove this, I probably don't want to try to prove it with a 10 by 10 square matrix. So let's keep it simple. Let's do it in R2. All right, so what I would be looking at is let A equal A sub 1, 1, A sub 1, 2, A sub 2, 1, A sub 2, 2. So I'd find the determinant of A. There's no reason why we have to reinvent the wheel. Now, technically there is a good reason why you have to reinvent the wheel. A proof, like a rigorous proof, you need to justify every single step, right? So that's the definition of reinventing the wheel. However, I'm going to let you off the hook with stuff like that and say that if I need the determinant of A, all I would have to do is diagonal down minus diagonal up. All right, you don't have to get into the permutations and all that stuff. You just say A sub 1, 1, A sub 2, 2, minus A sub 1, 2, A sub 2, 1. All right, so now I need the transpose of A. Easy enough. Well, easy enough if you remember what a transpose is. Swap rows with columns. So A sub 1, 1, A sub 2, 1. All right, so my first column became my first row. A sub 1, 2, A sub 2, 2. And then if I'm looking for the determinant of the transpose of A, it's diagonal down minus diagonal up. these are scalars, and scalars are commutative. Like when you multiply scalars, they're commutative. So these are actually equivalent, right? So therefore, now if you were multiplying matrices, like if A sub 2 1, A sub 2 2, instead of that it was like matrix A times matrix B, and the reverse. Well, that's not necessarily going to be true, but because they're scalars, it is following what you know of as the commutative property of multiplication from way back when. And so we have a proof. Now, again, it's only a proof for 2 by 2, but if it works for 2 by 2, then we can have faith that it's going to work for 3 by 3, 4 by 4, n by n, because really it's just, I'd be writing lots of dots, but ultimately it would amount to the same thing. All right, so an example of a proof, nothing too crazy. So if I put this one on the test, I don't know if I'm hinting at anything, honestly, because I can't remember what I put on the test as the proof, but maybe I am. Maybe this is the one. Put a star on it. I don't know. But if this showed up on the test, this is not something that you should be terrified of. Right? So this is a pretty nice one. Right? If 2 rows or columns of A are equal, then the determinant of A is equal to 0. All right? So what that would mean is I would have 2 identical rows and then just compute the determinant. So what I could actually do is define A, matrix A, as A sub 1, 1, A sub 1, 2, A sub 2, 1, A sub 2, 2, but then let A sub 2, 1 be equal to A sub 1, 1, let A sub 2, 2 be equal to A sub 1, 2, make the substitution, find the determinant, and you'll see that it equals 0. All right. The last one I think is probably the easiest one, because if a row or column consists entirely of 0, then diagonal down or diagonal up, either way, you're going to get 0. All right, so it's going to be 0 minus 0, which is equal to 0. All right. These are all, both of these in particular, this is just the fun one, but these in particular are very important to know, because a matrix is not going to be invertible if its determinant is equal to 0. All right, so this is something that we can, just by making a quick site identification, you look at the matrix and say, oh, I got a row consisting entirely of zeros. I'm not even going to bother trying to find an inverse of this. So you'd be in good shape. Right? Now, if you remember what the ultimate objective is when you're finding an inverse, you should know that anyway without having rules related to determinants, because when you augment your matrix to find the inverse, you're augmenting it with the identity matrix, with the goal being to transform your given matrix into the identity matrix. One's down the main diagonal. If an entire row or column is zeroed out, then there's no way you could ever make it a diagonal matrix containing all ones. Right? So you can kind of reason it out that way. But it's kind of nice. And then you have stuff like this, where if you know the fact, it's easy, because this is just telling me find the determinant of matrix A, because the transpose is going to have the same value. So diagonal down minus diagonal up. All right, so it just visually, I know that they're both going to be equal to the same thing. 4 on the down, 6 on the up, 4 minus 6, negative 2. All right, rows that are repeated value, containing repeated values, diagonal down 2, diagonal up 2. All right, and a row containing zeros, diagonal down, diagonal up, both 0. And so, again, not a proof, but a justification. All right, we also have some other nice ones. We have the it's similar to the anti-commutative property. If B results from the matrix A by interchanging 2 rows, then the determinant of B is equal to the negative determinant of A. Right? So if you swap any rows or columns in matrix A, then what you're going to end up with is a negation of the determinant. All right. If B results from A by multiplying a row or column of A by a real number C, so a scalar, then, and this is just a justification, then the determinant will be C times whatever it would be without that scalar being multiplied. All right, so if I have, you know, this matrix up here, A, -2, if I were to double, now I don't have to double every row, it's just saying I can double any row or column, and that will double the matrix, all right? The determinant of the matrix, all right? So very, very important to keep that in mind, because if I apply a scalar to the entire matrix, so if I multiply matrix A by 2, then I'm multiplying each row by 2, all right? That's not gonna be twice the determinant, all right? Because I'm double, 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 that's gonna be 8 times the determinant, all right? If B results from A by adding C times row A, so basically this is a row operation. So long story short, if I perform an elementary row operation, this one was just multiplying by a row by a scalar. This one is what we would do if we were performing the row operations by multiplying a row by a number and then adding it to another row. You get this relationship, and that's the determinants would be the same, which I think makes sense because the elementary row operations in general lead to equivalent matrices. The only exception is that middle one is the scalar one that does not, all right, necessarily do that. Right? You're actually changing the scale of the matrix, which, you know, you're changing the size of it, right? Even though it's equivalent in terms of the direction and the angle. Like if you plot a vector 1, 2, 3, for example, and then plot the vector 2, 4, 6, they have the same angle, same direction. One's twice as long as the other, right? So the value of each of those vectors are different. Their magnitudes are different. And so therefore the determinant, if I had that component, that vector making up part of a matrix, that determinant should be different. But if I perform this particular operation, it does not change the determinant, all right? So put a couple of stars on these bad boys so you can practice. They're good questions, but you know, they're also the kind where, you know, if time's a factor, you could probably bag these questions because, you know, even if like the first time you ever attempted these kind of questions were on a test, as long as you know how to find a determinant, you're fine, right? Because really all it's doing is justifying some rules, but yeah, the more practice you get, the better. Oh, that reminds me, I gotta send that up. Okay. Don't let me forget, before you leave, I typed up a set of suggested textbook problems, just like I did in the last unit. I had every intention of sending it out on a remind today, but then somebody was talking to me and I lost track of things. So yeah, I definitely want to send that out tonight. More examples, just more examples, more properties. Yeah, so determinant of AB, so the product of matrix A and B as a determinant. This I think is probably what you would have expected. Their determinants multiplied would be equivalent. But this one, this is a juicy one. All right, because this is what I was alluding to before. And so if you didn't quite follow what I was saying, then this is your way of picking it up. All right, now I'll actually take you through this example here. So these are, I'll put a star on this problem, but I'm gonna do H with you, right? Because that's a good one. I feel like I missed a star. I did. All right. So determinant of some scalar multiplied by A, because remember what I was saying, if you multiply a single row by a number, that is the scale factor of your determinant. Here we're talking about multiplying an entire matrix by a number, which means that what's essentially occurring is I'm multiplying each row by that number. And so it's going to have a compounding effect. All right. So diagonal down minus diagonal up for matrix A. I don't know what just happened there. Lord only knows. 4 minus 6, which is negative 2. All right. I'm doing the wrong one. I mean, the right calculation, just writing it in the wrong place.
Question, Professor.
Hmm.
All of these properties only pertain to an n by n matrix?
N by n, yep. So 4 minus 6, which is negative 2, that's the determinant of matrix A. Now, for matrix 100A, right? So that's what we would get if we ran through and multiplied every entry by 100. There's a couple of ways you can do it. One way would be to just do diagonal down minus diagonal up, which is what I'll do right now. But then I'll show you the other way of handling it. So we're doing 4 zeros, so 4d,000 minus 60,000. So we're looking at the matrix 100A being equal to negative 20,000. All right. So it's not just a simple matter of multiplying the determinant by 100. All right. Because what happened is I started off with matrix A. And so what we did was we multiplied the first row by 100. So just based off of that operation, the determinant of A must be multiplied by 100. I'll do that in green. Well, actually, that part I want to do in black. So, all right. So by multiplying any row by a particular value, you multiply the determinant by that same value. But because in order to multiply an entire matrix by a scalar, I have to multiply each row by that, I actually have to multiply by 100 twice. So that means that that separate calculation has to occur. So that gives me 10,000. And since we had already determined that matrix A had a determinant of negative 2, 10,000 times negative 2 would give me the negative 20,000. All right. So that allows us to kind of streamline the process. So what I would do is if I were given, let's say, a 5 by 5 matrix, and I wanted to multiply that matrix by a number, I would actually be multiplying the determinant by that number to the 5th power. All right. So the power is consistent with the number of rows or number of columns, depending on what you're multiplying by. All right. So yeah.
Why is with the 3 and the 2?
Oh, Lord only knows. I'm definitely going to be locked in now. Oh, no, no. So 1, 3, 2, 4 is what it was. Funny thing about consecutive values, I just want to write them in order, you know, it's crazy. All right, so I'll put a star on the next one. Kramer's rule, we're gonna. Did I really just put skip? I actually don't. Really like it. I'm sure Kramer would be very offended, but I don't care. I don't care about him. So, the last topic that we're going to talk about is called the cross product. It's actually related to the concept of determinate, right? And so there's lots of value to this. So cross product is it's a form of multiplication, vector multiplication, that guarantees that you're going to generate, given two vectors, a third vector that's orthogonal to the first two. All right. So the only issue is orthogonal could be going, if this is a horizontal pair of vectors, orthogonal could be going up or it could be going down. All right. So it depends on the situation. Sometimes you want the one going in the positive direction. Sometimes you want the one going in the negative direction. But ultimately, we're guaranteeing a vector that will be orthogonal to the first two. All right. So the question would be, well, how do we go about doing that? Well, it's completely algebraic in terms of the derivation. We know that if we find the dot product between two vectors, that's going to, if the dot product is equal to 0, then those two vectors are orthogonal to one another. But how does that equate to the third vector? So what I'm going to do is I'm going to just draw two vectors that are kind of floating in space. Poor quality vector. There we go. And actually it's kind of cool because, I mean, this is what I'm going to try to draw in a second. That's the app trying to line me up. But in doing so, it's creating an orthogonal vector. Except it goes away the minute I release. I think I can handle that, actually. I think that might be in my wheelhouse. Look at that. It's like it was giving me a little tip. How do we do that? All right, so we have vectors u and v. And then we have the orthogonal vector, which would be w. This has to be perpendicular to these two given vectors. All right, so I have a field that spans the two vectors. That third vector needs to be orthogonal to that field. All right, so cool. Now we actually just got to carry it out. So if I dot u and w, I should get a result of 0. And if I dot v and w, I should get 0. All right, because u should be orthogonal to w, v should be orthogonal to w. They're not, u and v, not necessarily orthogonal to each other. They could be, but that's not a requirement of this. All right, so now we just got to dot it out. So u1, w1 plus, so we're creating a linear combination, u2, w2 plus u3, w3 equals 0. And then for the second one, v1, w1 plus v2, w2 plus v3, w3 equals 0. All right. So pretty greasy mess here. I have a system of equations, the system of equations in lots of variables. Well, regardless, I mean, I'm going to try to eliminate something. I mean, obviously, I don't want to say obviously, but I think it's probably a safe assumption that we probably don't want to try to row reduce this. Just a thought. So we'll go about it algebraically. So what I'm going to do is I'm going to just try to cancel a term. So I got my sights set on these two. I want to get rid of those. Why those? Why not those? Doesn't matter. Just try to get rid of a pair. So in order for that to happen, I need them to match up. Well, the first set of factors is missing a V3. So let me multiply the first equation by V3. The second set of factors is missing a U3, so let me multiply the second equation by U3. All right. So I'd be looking at U1, V3, W1, plus U2, V3, W2, plus U3, V3, W3 equals 0. Then U3, V1, W1, plus U3, V2, W2, plus U3, V3, W3 equals 0. All right. So we're in good shape. We have matching factors. So if I subtract the second equation from the first one, or, you know, instead I could have just multiplied through the negative U3 and then added the two, but I think it amounts to the same thing. I mean, I know it amounts to the same thing, but in terms of difficulty level. All right, so subtract the second equation from the first one. We know that these two are going to cancel away. So I'm not even going to worry about that. I'm going to have U1, V3, W1. Now we don't have any matching terms, so we don't have any like terms, so it's not like I can combine anything. So I can just do pretty much everything I see here. I'll do it across the top and then across the second row. So U2, V3, W2 minus U3, V1, W1 minus U3, V2, W2. And that would result in 0. All right. So, you know, there's different approaches that you could take, but ultimately, I got to try to solve for one variable in terms of the others. And it's just a question of, well, which one or which ones. So I can regroup. It looks like I just have W1s and W2s. So what I can do is reorganize a little bit. So here's my W1s. So I'm going to rewrite that as U1 V3 minus U3 V1 W1. All right. And then plus the others, which would be U2 V3 minus U3 V2 W2. Result is 0. All right, so what we're getting is a linear combination of W1 and W2. And so from that, we can kind of infer what the other possibilities would look like. So you would say, well, what if I had opted to cancel out, let's say, instead of the W3, let's say I canceled out the W1, what would it look like? What would it look like if I canceled out the W2? Right? Essentially, it's going to be the same structure, except you're going to have different bits and pieces. All right? So you see here, I have a W1 and then a U1 V3. You know, it's a question of, is there a way that I can get, knowing this, get this array of values? All right? So what I'm going to ask you to do on your own is, well, I won't write it, I'll just say it. Go back to this pair of equations and eliminate, systematically, eliminate the other two terms. So first, multiply through so that you can eliminate the first term, work it out so that you can get the next expression, and then do it so that you're canceling out the second term. I'll kind of steal my own thunder again a little bit to say that this is going to lead us to what's known as a cross product rule, and there are shortcuts to that rule, which I'll talk to you about in a minute, which is related to the cofactor expansion. Right? But I want to see if you can come up with this on your own first, because this is the pathway that'll kind of get you there, and if you do that work, then I can get you the rest of the way. All right? Ultimately, you're looking to get these rules, right? And so that would be, and you can see, we pretty much have this there already. It's just a question of how would you go about getting the other component, right? We got 2 out of the 3 components, how would you go about getting the third one? So we'll revisit that next class, but for now, what we're gonna do is we're just gonna actually find some cross products, right? So using the technique. So again, it's going to give us a third vector that's guaranteed to be orthogonal to the first 2. So process-wise, it's going to be, you're going to see it's a little bit fishy, only because we haven't invented the entire formula yet. But at this point, we're just going to go based off of what we see here. And I just, yeah, you see, it was an edit that I meant to make. Okay, so somebody gets typo bonus here. The shortcut rule should be right up here after the not so shortcut rule, because I don't like doing it for the sake of doing it. But anyway, so I'm going to apply the shortcut rule immediately and show you how it plays out. All right. So we have vector u and v. What we do is we create a matrix that we're going to find the determinant of. The first row of the matrix is going to be ijk. And next class I'll talk to you about why that's the case. U is going to make up the second row. So we're working with row vectors now. The way that the shortcut comes into play, it requires you to have vectors written in row form. So that's vector u and then vector v. Okay, so we've been representing vectors as column vectors all this time, but we didn't always have to. It's just a lot of the strategies that we use to perform operations just make it more convenient to think of them in terms of columns, right? But you can write vectors as rows of a matrix or columns of a matrix, because a matrix really is just a way of organizing your information. As we learned last class, maybe a vector isn't even something that's geometric. It could represent the percentage of an economy that's going to different sectors, all right? So at this point, most people are fine with, oh, okay, I didn't know that. I can write them as rows instead of columns, right? But there is a justification for that. Right, so what we do is we use our cofactor expansion across the first row, all right? So this is my a sub 1, 1, and we have a sub 1, 2. I'll do that in a different color, purple. And a sub 1, 3. All right, the j values are 1, 2, and 3. If I go -1 to the 1 plus 1 power, I'm going to get -1 to the second power, which is a positive result. So I should be starting off with a positive and going negative and then back to the positive, just like every other cofactor expansion problem. Then I take my I, All right, the I is the first entry. I put it at the end because if we're going to use IJK notation for our final answer, it would make sense to have something in front of the I. All right, then the J, and then the K. Same deal. All right, so if I ignore the row and column that contains the I have a matrix 2, 5, 0, negative 3. If I ignore the row and column containing the J, purple is what I should have gone with here. I'd be looking at negative 1, 5, 4, negative 3. And if I ignore the row and column containing the K, I'll be looking at negative 1, 2, 4, and 0. Negative 1, 2, 4, and 0. All right, so basically what I'm doing here is kind of manufacturing a situation where I'm writing a linear combination of I, J, and K where the weights are the determinants along the cofactors. All right, so diagonal down is going to give me a negative 6 minus 0, so just the negative 6. For the second one, diagonal down will give me a 3. Diagonal up gives me a 20. So 3 minus 20 is negative 17, but I have a negative on the outside, so positive 17. And then the last one, poor quality plus sign. See if I can, yeah. The last one is just a negative 8. So minus 8k. And so what this is the vector that is orthogonal to the two given vectors. All right, guaranteed. All right.
So a negative 8, no, isn't it 8 minus 0?
It's 0 minus 8. Diagonal down minus diagonal up.
Oh,
So 0 and then 8.
okay,
Okay, so now we have a way of figuring out what's known as a normal vector. All right. So normal vector is orthogonal to the given vectors. And we actually define the equations of planes based off of the normal vector, right? So this is an incredibly important piece of information, because when we talk about solving systems of equations and it's looking for the intersection of two planes, yeah, that's all well and good, but how do you come up with the equation of a plane to begin with? Well, as long as you know two vectors that are living on the plane, you could figure out the normal vector. That normal vector actually defines the plane, right? Because it's all, and you covered this in the tech assignment, as the normal vector goes, so does the plane. So if the normal vector is of two planes, for example, if they're going to intersect, then the planes are going to intersect. If they're going to be parallel, then the planes are going to be parallel, right? So a lot of things going on there, right? So very, very important that we have a good grasp of this. But you can see here, you know, like the notation is a little different, but this is the concept of finding a determinant, right? There's really nothing different here than the process that we use for finding a determinant using cofactor expansion. But remember, before I was saying that we were learning it by hand for a purpose. There is no button in your calculator that'll find the cross product for you, all right? So, I mean, there are programs you could write programs, or you can download programs or copy somebody else's programs that'll do it for you, but those are a little bit harder to come by. number 2, I'll leave that for you to do. It asks you to find the cross product of V and U, and then U and V. So it's telling you to swap the order. I mean, all you have to do is flip ahead and you can see what the shortcut would be for this, because there is a relationship between the cross products of U and V and V and U. They're not going to be the same, but there is a relationship. All right. So what I'm going to do, and this will be, oh, well, it's like staring right at you, so try not to look at it. I'll take you through a case where we write the equation of a plane, and that'll be pretty much it for the unit. Maybe we'll do another example afterwards, but it'll be the last major concept. Okay, so if I want to write the equation of a plane containing these 3 points, first I'd have to define a vector, a pair of vectors that contain those 3 points. Right? So I'm gonna pin it. I'm gonna pin both of my vectors at the same location. It really doesn't matter where, so I'll pin them at 3, 1, 4. All right. Personally, I like to name my points just to kind of keep it organized a little bit. So I'll call this one P, I'll call this Q, and I'll call this R. Now the points are listed up here, but it's better to do it based off the diagram, because then it's pretty obvious that I'm looking for vector PR and vector PQ. Correct. Yeah. You'll get the same equation of the plane when all is said and done. All right. So PR so 2 minus 3 is -1. 7 minus 1 is 6. 1 minus 4 is -3. PQ, -1 minus 3 is -4. -2 minus 1 is -3. -3 minus 4 is -7. All right. So what I need is the normal vector, which is the cross of P, R, and PQ. Determinant, not a normal vector, ordinary vector. So we know the signs are going to alternate, positive to negative, back to positive, and we're going to have a coefficient of I, J, and K. So yeah, I mean, it's the concept of writing the equation of a plane. It's just in the past we would have the normal vector that we could work off of. Now we just have to invent that. But once we have it, it's going to be pretty easy, right? So for I, diagonal down would be -42. Diagonal up would be a 9. So -42 minus 9 is going to be -53. -51? -51. right, for J, diagonal down is going to be 7, diagonal up is going to be 12. So 7 minus 12 is going to be negative 5. So negative negative 5, so plus 5. And then for the K, ignore the K row and column. So I'm looking at diagonal down, negative 1 times negative 3 is positive 3. Diagonal up, negative 24. So 3 minus negative 24, so 3 plus 24 is going to be 27. All right, so, barring any mental math mistakes, which is always dangerous for me. And also, you'll notice how I didn't bother writing out the cofactors. I didn't bother writing out the 2x2 matrices. You just do it on the fly. There's nothing wrong with that, unless, I'll just put it this way. If I were in your position taking a test, I'd probably write the 2x2 matrices out because I'd be afraid that I would screw something up just by rushing. But if that's not something you're concerned with, then it should be fine.
Can you check the answer in here?
Say it again?
Can you check your answer?
The only way, unfortunately, to check it would be to pop it into GeoGebra, which works now, works when you're at home, but doesn't work on the day of a test. So practice now so that you could just have faith the day of a test that it's all going to come out in the wash. All right. So that's the one unfortunate thing. So my normal vector here, n, is going to be equal to negative 51, 5, 27. All right. So the equation of a plane, the general form, which is probably the least useful way of representing it, ax plus by plus cz is equal to d. All right, but then d is something else entirely. All right, so there's calculations involved in that. The variation of the plane equation that I prefer involves dot products. So this is good, it's okay, but the better option would be to say the dot product of ABC and XYZ equal to the dot product of ABC and the relevant point along the plane, x sub o, y sub o, z sub o. Right, so this is my normal vector. X, y, z, that's going to be part of it. You have to have your variables in your final answer. So x, y, and z are going to be there, so we don't really need to find that. You can go x1, x2, x3 if you want, but I think this is better. So this is still the same n, and this is some point that is along the plane. So point P specifically in this case. So we're back to n over here. It has to be the point that is used to generate the normal vector. All right. So it has to be a point on the plane as well as on the normal vector. All right. So it has to be P. You can't just choose one of the other two. Now, if I pinned my two vectors at Q, for example, then I would use this coordinate, or this ordered triple. If I use R, so if I extended from R to P and then R to Q, then this would be the relevant point. All right. So in writing the plane equation, it's negative 51, 5, 27 against x, y, z. And then negative 51, 5, 27 against my point P, which is 314. All right, now these are dot products. I didn't include it there because it's kind of implied, but I'll put them in anyway. All right, so left-hand side, negative 51x plus 5y plus 27z. Right-hand side, you just got to do the work. We're looking at, was it negative 153 plus 5 is negative 148 plus 108. So negative 148 plus 108 is negative 40. All right, so that's entirely too dangerous. I just did that way too fast. So definitely double check me on that. 54,108. 113 minus 153. All right, well, you'll let me know if it's wrong. All right, so that's right. Oh, look at that. Yay, I did math right. Happens every once in a while. Broken watch is right twice a day. So that's our plane equation. Now, again, if you pinned your two vectors at R or Q, going through this process would have given you the exact same equation. Might have had a slightly different look. Maybe it's the negation of this entire equation, or maybe it's double or something, but it'll be equivalent. And that's the important thing. All right. So now if you think about it, a question on the test, for example, could say something like, find the intersection of the two planes, but maybe one of the planes is given as a set of coordinates rather than just a defined plane. So the extra step would be going through the cross product approach to come up with the equation of the plane itself in order to then find the parametric intersection between the two planes.
So the negative 40, that's the determinants, or?
That's the D value, the right hand side. So it actually doesn't, that part of it doesn't have anything to do with the determinant. It's the cross product that is the determinant. All right. This is actually the dot product between your normal vector and a point, the vector passing through a point. All right. So, and that's a key thing. I'm actually glad you asked, because 314 itself is not a vector, but what we're dotting this against is the vector that would have an endpoint at point P, 314. Right. So it's probably not overly necessary in terms of getting the question right, but in terms of understanding how it's legal to just take a coordinate in order triple and write it as a column vector, I think there's probably some value in that conversation. All right, so properties of the cross product, there's a bunch of them. Some of them are just straight up common sense. And again, I teased one of them on the previous page, and it's like right there staring at you, so that should be easy enough. Distributive properties, common sense, multiplying by a constant, maybe, kind of, it just looks weird. When you're multiplying, if you have two factors and you multiply those factors by a number, you do it a couple of ways. You can multiply the two factors together and then multiply the number through later on. Or maybe you just multiply one of those factors by the number and then take the result and multiply it through later on. But the one thing you don't want to do is if you had something like 2 times 3 times 4. So 2 times 3 times 4, just numerical values. You would not distribute the 2 to each part and then multiply, because that's the same as saying, so this is not the same as what you would get if you were to just multiply 2 times the 12 and get 24, all right? Because you would actually be scaling this up by a factor of 2, all right? You would be getting 6 times 8, 48, not equivalent, all right? So that's all this rule is saying. It's something that you already know. Cross product with the 0 vector. Now, mathematically, multiplying by 0 seems to make sense. The result's going to be 0. Visually, what this is saying is that you have a vector that's going off into space. If you cross that with a 0 vector, so a vector that has no magnitude, well, what's going to be orthogonal to that? I mean, it's not a vector. It's not going off. It's violating the rules of the cross product. You need to have two non-zero vectors in order to have a third one that's orthogonal to both of them. How are you going to be orthogonal to a point? Wouldn't every single vector in creation be orthogonal to a point? Yeah, so that I think conceptually makes more sense. This one's weird. Cross product of a vector with itself. Also could, this is the kind of question, thinking to what could be a proof question on the test. This is a nice, elegant one. A vector in itself, the cross product, right? Because this goes back to the idea of the determinant. One of the properties of determinants where if the rows are identical, the determinant's going to be equal to 0. Since a cross product is just another way of representing a determinant, this should make sense. And then the last one is a triple scale, or a scalar triple product, or a triple scalar product. You can say it either way. That I'm actually going to save for the next unit, all right? Because that allows us to find volumes of, we find areas of parallelograms in 2 space. We find volumes of parallelepipeds in 3 space. All right, so that's something that I'm going to save for the next.